Hi everyone, my name is Chelsea Finn. I'm an assistant professor at Stanford University, and today I'll be talking about learning structured exploration strategies. As a means for an introduction, my lab and my research is generally interested in how we might develop broadly intelligent behaviors through learning and interaction. And a key component of this goal and of this kind of question is actually studying robots in the real world. Robots that look like this, that can insert objects into particular holes, can learn by watching people do tasks, can learn long horizon tasks such as stacking blocks into towers, or can figure out how to use objects as tools to accomplish certain goals. Now, you might wonder, especially at a computer vision conference, why we might consider studying robotics. One of the reasons why I'm quite motivated to work on robotics is that I think they can teach us things about artificial intelligence. In particular, robotics is a particularly challenging problem because robots are faced with the real world. They must generalize to different tasks and different environments in order to be useful. And the supervision really can't be taken for granted. It's not clear what the supervision should be for robotic agents in the world. And so I think that if we can build intelligent robots in the real world, we can convince ourselves that we've solved some important problems in artificial intelligence. But of course my goal isn't to convince you to work on robots. My goal in this talk is to provide a bit of a perspective on some of the things that we've learned when studying these challenging problems, and some of the challenges that pertain to developing intelligent robots in the real world. Now, what I'd like to talk about in this talk is one fairly specific problem, which is how should a robot explore in its environment? Now, of course, there's a breadth of work in this area, especially in the reinforcement learning community, that has made significant progress on this problem. But the approaches that we've seen haven't been quite as satisfying for looking at problems in the real world in robotics. I would say that there's probably two camps of approaches in the reinforcement learning community for solving the exploration problem. One is trying to explore specifically in the context of maximizing a reward function. This is essentially kind of a standard version of the RL problem where you want to minimize regret, where you are optimizing some reward objective, maybe with some additional exploration bonus or something else that's accounting for your uncertainty in your policy. Now, this approach has been quite successful. It actually works quite well and has been shown to solve various things such as Atari games. And it can scale in principle to fairly complex environments by focusing on that reward signal. But the downside to this approach is that shaped rewards, which is often what these kinds of approaches require, rely on very detailed supervision from experts. And even experts have found it quite challenging to actually engineer reward functions that are successful for these kinds of problems. And further beyond the problem of reward engineering, this approach often leads to exploration that's specific to one task and is useful for that one task, but may not be useful for a breadth of tasks. So that's one approach that perhaps isn't too satisfying in the context of robotics. The other class of approaches is what I'll call simply to explore everything. This includes novelty-based approaches such as curiosity and count-based exploration that tries to explore anything that's novel to the robot, and also approaches that try to cover the state space by, for example, maximizing entropy or trying to match some kind of uniform density over the state space. Now, these approaches are quite nice in the sense that they're much more general. They'll lead to data that can be used for a breadth of tasks, and they don't require any supervision to be provided to the robot, which means that they're quite scalable in terms of the supervision that's required. However, it's very challenging to apply these approaches in complex real-world environments. For example, even an environment that looks like this, which is a robot in a lab environment with a bunch of different objects in front of it, these approaches struggle precisely because they're trying to explore everything about the world and not just the things that matter, such as the objects. And we've actually ran kind of state-of-the-art exploration algorithms in this kind of setting, and they tend to struggle, at least in the amount of time that we have patience to run them for. So in this talk, I'd like to focus on whether we can build an exploration approach or a set of exploration approaches that are a bit more satisfying for actually a real world interacting with the world and perceiving that world. And in particular, if we can explore in a structured manner without the reward engineering of the first class of approaches and while achieving greater scalability compared to the second class of approaches. Okay, and in particular, when we're studying this question in this talk, I'm going to go over 3 case studies, per se, that try to study different ways that we might be able to accomplish this for different goals. So in the first, we'll look at exploration for long horizon tasks, then we'll look at exploration for new environments, and lastly, we'll look at exploration for being able to manipulate different new objects. And for each of these, we'll leverage different bits of supervision to try to guide the exploration process. But in each of these cases, we want the supervision to be something that can be provided not by an expert, by someone who that requires essentially less engineering. So in the first case, we'll look at leveraging language for solving long horizon tasks. In the second, we'll look at leveraging very simple supervision, such as sparse binary rewards or different identifiers for different environments. And lastly, we'll look at leveraging diverse demonstrations. And the ultimate goal in all of these approaches is to leverage that supervision that's provided, as well as the robot's experience, to learn a breadth of complex tasks. So not just a single task, and not just very simple tasks. We're going to be considering multiple tasks that require the robot both to perceive images of the world and act using that perceived state of the world. Okay, so let's first look at this first case study of trying to explore for long horizon tasks by leveraging language. And in particular, we're interested in the question of, can the compositional structure of language enable agents to perform long horizon tasks? Now you might ask, well, why use language? Specifically from a reinforcement learning point of view, it may seem like language might just make our jobs harder, but language has a number of benefits, including the compositional structure that is kind of inherent to many forms of language. It's also general to a wide range of behaviors and tasks. It isn't kind of specific to one set of tasks. And language also affects how humans think and reason, and there's evidence for this in the cognitive science and neuroscience literature. Now, in this case study, we'll specifically be looking at long horizon tasks, like I mentioned before, and rather than relying on very shaped reward feedback, we're going to consider sparse binary rewards for manipulating different objects, and we're going to build an environment inspired by Clever. So the ultimate goal that we'll want to try to accomplish is to arrange objects, order objects, or sort objects in different ways, in both kind of a basic version and a diverse version of the environment. And we're also going to be using the language that is generated by the Clever engine. So we won't yet be using natural language, but in principle, I think that this sort of approach may also scale to natural language. Okay. So the overall approach for this that we'll use is actually quite simple. The first thing that we're going to do is train an instruction condition policy to perform low-level tasks like pushing an object in front of another object or pushing an object to the side of another object. And then once we train this instruction condition policy, we'll then train a high-level policy to act in the space of language. Essentially, this high-level policy is going to output instructions that are provided to the low-level policy to accomplish longer horizon tasks. And by acting in this higher level space of instructions, the high-level policy can actually explore much more effectively through the space of these semantic tasks that are encoded with language. Okay, so let's kind of break down these two steps a little bit further. So the way that we're going to train an instruction condition policy is first we're going to make one assumption, which is that during training time, we're going to assume the ability to sample language questions and get answers for those questions. So we'll essentially be able to query a question answering model similar to the models that are trained on Clever, for example. And then we'll give a sparse reward to the agent for whether or not an instruction is achieved or not. So for example, if this is the current state of the world, and this little white ball is the thing that the agent can control to push different objects, we'll give an input instruction, and this input instruction will actually be in the form of a question, and the goal of the agent will be to try to make this question true. So in this case, the question is, are there any matte cyan spheres to the right of the red ball? Then the robot will execute, or the agent will execute an action or a sequence of actions, such as something like this, that leads to this outcome. Of course, this doesn't satisfy the input instruction because this didn't make it such that there was a cyan sphere to the right of the red ball. But it does actually, in hindsight, accomplish another instruction, which is this one right here, which is that now there's a cyan ball that's in front of the green sphere. So what we can do is store the data of the original instruction and experience, but also relabel the transition with this new instruction that's true and add that to the replay buffer as well. And by adding both of these, we actually get example of a failure from the current policy, but also an example of a success of what it did successfully and correctly in hindsight. And this can actually provide supervision and provide guidance to the agent much more effectively than if we only gave it the sparse reward of the initial instruction of it constantly failing. Okay, and we'll call this hindsight instruction replay. It's quite similar to hindsight experience replay, except that we're relabeling using language instructions, which in many ways is actually much more general because we have this higher level space, or it's much more desirable in the sense that we have this higher level space that we're providing instructions and relabeling with. Okay, so now that we train this instruction condition policy, we're then going to train a high level policy to act in the space of language. And the way that this works is that we have this high level policy in yellow that outputs, that selects an instruction G, and this instruction is passed to the low level policy in blue, and this low level policy outputs actions for a fixed horizon in the environment, and then the high level policy then gets to select another instruction. And by doing so, the high level policy leverages the low level policy to explore in this more semantic space of language. So we get these kind of temporally extended exploration strategies, and we then train this high level policy with sparse reward long horizon tasks. So essentially you can view this high level policy, or this overall overarching structure, as some form of reasoning in the space of language. And one kind of side benefit of this is that it's also actually quite interpretable. So you can see if the high level policy outputs, you can see essentially what it's thinking, if it's outputting a high level instruction that, that makes sense, or if something that doesn't quite make sense. So we refer this overall approach as hierarchical abstraction with language, so we'll refer to it as HAL in the legends and the experiments. Okay, so in our experiments we wanted to study two questions. The first was, how can we evaluate if compositionality of language is actually useful and important compared to simply using one-hot identifiers, for example, or other typical kinds of approaches for this. And so to do this, we're going to compare to several different methods. One is simply just flat double DQN training. The second is the same hierarchical RL approach, but with a one-hot abstraction rather than a language abstraction. And then the last thing that we wanted to look at was hierarchical RL that's still an abstraction of language, but to try to kind of give it a non-compositional representation of that language instruction. And to do this, what we did is we trained a seek-to-seek autoencoder on the language instructions, and then we used the bottleneck layer of this autoencoder as an abstraction. And so what this essentially controls for is it controls for the amount of information that's given to the agent. So the agent gets the same exact instructions, but now this learned representation may not actually exhibit the compositionality that the original language instruction had. And then lastly, we also compared to some prior hierarchical RL approaches that try to learn a representation end-to-end rather than using something like language. Now, what we find is that first we can look at the low-level policy training, which is just training the instruction following policy. What we find here is that even before we move towards the temporally extended exploration with the high-level policy, we see a significant difference between our approach, which is conditioning on instructions and using hindsight relabeling, and that's shown in blue, compared to both the non-compositional language representation, which has the same amount of supervision, and compared to these one-hot representations as well. So it's pretty clear that compositionality is quite helpful for learning these different tasks. And then if we move towards kind of a full hierarchical RL setup, for example, the object sorting task, where we have an initial state like this problem is extremely challenging because we're looking at a setting where you have to perceive the raw RGB values of these images, and you have to figure out how to push different objects in such a way that you get the binary reward of completing this task successfully. And here's one kind of rollout of the high-level policy. So first it tries to move, it instructs the low-level policy to act such that there's a cyan matte sphere on the left of a blue rubber sphere. And the result of this is a state like this, where there's a cyan sphere on the right of, or on the left of a blue sphere. Then it tries to instruct the low-level policy to put a green rubber ball in front of the blue rubber ball, and we get an action that looks like this. Next, it gives it an instruction to move the cyan matte sphere behind the green rubber sphere, and then we get something that looks like this, so it moves the cyan sphere over. And then lastly, it executes one more action, which is to put the purple matte sphere in front of the red matte sphere, and we get something that looks like this, that has successfully sorted the objects into the same configuration as the task. Okay, great. And quantitatively, we also see pretty strong benefits using this approach. So even in a non-vision version of this environment, HAL is able to learn quite stably, as shown in blue, whereas double DQN is able to learn in some environments, but not as stably, and not in all environments. And in vision-based environments, HAL is really the only method that's able to learn effectively. And so we see these three curves correspond to the three high-level tasks, whereas prior approaches are down here. Okay, great. So the takeaway here is that language provides compositional structure and supervision that's needed for solving multiple complex long horizon tasks. So while this has been quite successful for long horizon tasks, this doesn't necessarily give us a means to explore when placed in new environments. So this is what we'll look at next. And specifically the problem setting we're going to be looking at here is we're going to assume that we've had the ability to learn tasks in some previous environments, and our goal is to quickly learn that same space of tasks in a new environment. For example, maybe we trained a robot in a factory in different kind of kitchens in a factory to cook different kinds of meals. Then we want to deploy the robot into someone's home and have that robot cook meals in that kitchen. So there's a number of ways that you could try to approach this problem, but we're actually going to frame this as a meta-learning problem, where we're going to have the agent learn how to learn each of the tasks in these environments, such that when given a new environment, it's given one exploration episode to explore that new environment, and then we want it to be able to execute different tasks in that environment. Okay. So now the big question here is, how should you actually spend this exploration episode? What about the environment should you explore in a way that allows you to effectively perform the tasks? Now, in principle, existing meta-RL approaches already allow us to solve this problem, but there's a bit of an issue that makes it pretty challenging to apply to complex exploration problems. And this arises because of a coupling problem between exploration and execution. So a common approach in meta-reinforcement learning is to try to jointly optimize exploration and execution behaviors end-to-end with the goal of maximizing reward at the execution time. And this approach of optimizing both of them end-to-end leads to a bit of a chicken and egg problem, where you need to kind of figure out you need to learn how to cook, and you also need to learn how to explore and find ingredients. And if you haven't yet learned how to explore, you don't know how to find ingredients, then it's going to be pretty difficult to learn how to cook if you don't know where the ingredients are. And likewise, if you don't know how to cook well, and you're training exploration so that your execution does well, then you're going to have low reward for any exploration strategy that you produce. So essentially there's this coupling problem where learning good exploration and learning to execute tasks depend on one another. Now, the key idea in this study is that you can actually independently learn exploration and execution in a way that breaks this coupling. So in particular, what we'll do is we'll first learn to execute tasks, and this will allow us to identify key information about the environment that's needed for those tasks. And then we'll learn to explore by trying to recover that key information. So in particular, what we're going to do is we're going to assume that for each environment, we have an identifier, like a one-hot identifier, for example, for that environment. So that's what we're calling the problem ID here. And we're essentially going to learn a policy conditioned on that identifier of the environment that can execute the different tasks that we care about. And we're going to bottleneck the representation so that any extraneous factors about the problem ID are thrown away, such as the color of the wall or the decorations, leaving only the bits of information that are relevant for the task, such as the ingredients. And of course, this is an example where the problem ID consists of these different components, but in practice, this can really just be a one-hot vector of different bits. So the first step is to learn essentially this environment condition policy, and then the second step is to train an exploration strategy that tries to recover exactly information about Z. And we can do this by training a policy that produces trajectories that have maximal mutual information with this environment encoding Z. Essentially, in this case, the reward will correspond to information gain about Z. And then after meta-training and meta-testing, we can then run this exploration strategy, produce an exploration episode which has information about the environment, and then pass this to the execution policy that can then use what it learned previously to execute the task. So we refer to this approach as decoupled reward-free exploration and execution in meta-RL, or a DREAM, in the sense that we're kind of decoupling the execution part and the exploration part. And we find this actually works quite well in practice. So we ran a number of experiments in the paper, but I'll focus on the most complex experiment, which was a sparse reward 3D visual navigation task. And in this case, the goal, different tasks corresponded to going to a key, a block, or a ball, and in different environments, you either needed to go to the blue objects or the red objects. And the color of the object that you're supposed to go to is actually written as a sign on the wall. And the agent starts on the other side of the barrier so that if it wants to explore, it needs to actually go around the barrier and read the sign. The agent receives pixel observations as input and only a sparse binary reward when it actually accomplishes the correct task. Now what we find is this is the kind of exploration policy that it learned, where it is able to figure out that it should go around the barrier and ultimately go and read the sign on the wall, as shown here. This is a very kind of directed exploration strategy that's specific to this class of environments and tasks. And then during the execution episode, we see it's able to leverage that information to go to the key, the blue key in this case, by leveraging the information that it needs to go to blue objects here. Okay, and then quantitatively, we see that DREAM achieves near optimal reward on this environment, so it approaches this purple line right here. We also see that existing state-of-the-art meta-RL algorithms, including RL squared, import, and very bad, perform pretty poorly because of this coupling problem, and they aren't able to figure out a good exploration strategy. And we also see that alternative exploration strategies, such as Thompson sampling, do not learn the optimal exploration strategy. And this pink line right here is basically showing an upper bound on the Pearl algorithm, which leverages Thompson sampling in order to explore for new tasks. So essentially the takeaway here is that we can actually learn pretty complex structured exploration strategies via meta-learning, and we can do so leveraging only environment IDs and sparse task rewards. So this is quite nice. Cool. So next I'd like to talk about whether we can actually learn exploration strategies that are useful for a real robot. In practice, these previous approaches could also be applied to a real robot, but it's not something that we've gotten to yet. And in this case, we're going to specifically be focusing on generalizing to different kinds of objects, and doing so in a way that leverages diverse demonstrations. Now, before I start and talk about this work, it's worth mentioning that leveraging demonstrations for exploration is by no means a new idea. People have been using demonstrations to accelerate reinforcement learning for many years, especially in the context of robotics. What's going to be different here is that the demonstrations won't just be for a single task. The goal will be for these demonstrations to demonstrate kind of broadly useful exploration strategies for a certain class of tasks, in this case, the class of tool use tasks. To study this approach, we're going to build upon a model-based RL approach that typically corresponds to collecting random data in the environment, using that to learn a video prediction model that predicts what the future will look like based on the actions the robot takes, and then plans using that model to accomplish certain goals. Now, these random exploration strategies often aren't particularly successful for learning more complex tasks. And this is where the demonstrations are going to come in. So the first thing we can do with these demonstrations, of course, is to use them to improve the model, to give additional data to the model, but we can also use them to help with exploration. And so what we're going to do for that is we're going to fit a model of the kinds of actions the demonstrator will take conditioned on the initial image. And we can use this to direct the data collection process to actually explore the kinds of things that humans might do. And we can also use it to guide the planning process when actually thinking about what actions the robot should consider taking. Now, as I mentioned before, we're going to consider a more specific class of problems, and in particular, we're going to look at a variety of different tool use tasks, where we want the robot to be able to pick up a tool or the handle of a tool, and then use that to push objects into different positions, or otherwise kind of affect the environment. Now, once we fit an action proposal model to these demonstrations, we can also visualize the kinds of things that it thinks, and by actually running those action predictions through our video prediction model, and we get behaviors that look like this. So we essentially see that the robot has learned different kinds of exploration strategies that correspond to picking up these pieces of trash, picking up an object and moving it around in a certain way, such as to clean the surface, or maybe the action proposal model isn't perfect and it misses the object, and the video prediction model can actually tell that it didn't quite make the object. So essentially these demonstrations provide supervision about object affordances, about kind of the handles of tools, and this can be used to guide the exploration process towards these kinds of tasks. Great, so that's generally how we're going to leverage these demonstrations. And the way this works at test time is we specify a goal by selecting where objects should move. We then run visual planning guided by the action proposal model with respect to this goal, and then execute those actions on the robot, essentially execute the actions as a result of planning to get something that looks like this. Now, in our experiments, we wanted to specifically look at not just one task, of course, but a breadth of tasks. So we looked at something like being able to solve a new task that wasn't in the demonstrations, such as picking up a brush and using that to sweep objects into, or push objects into a dustpan. We also looked at a setting where the robot needed to bring this blue object closer to itself, and we constrained the robot's action space to this green rectangle so that it's forced to figure out that it needs to use the hook in order to accomplish that task. The robot could also figure out how to use tools that it's never seen before, such as a sponge, to wipe objects off of a plate. And the reason why it can generalize to new objects is precisely because we had a diverse demonstration data set, and we also had a diverse set of random data that was also used to train the model. The robot can also use unseen objects that are not kind of conventionally thought of as tools, but can be kind of improvised as tools, in this case, like a water bottle. And lastly, by using a planning approach, the robot can figure out when it makes sense to use a tool, such as when there are two objects that need to be pushed, and also when it makes sense not to use a tool, where it's more efficient to simply move the object directly. So it isn't relying precisely on just the demonstrations in order to solve these tasks. And then finally, quantitatively, we also see significant improvements with this guided visual foresight approach shown in purple compared to other approaches that only use the demonstrations or only use autonomous experience. So essentially, we're leveraging these demonstrations effectively to guide exploration and see kind of significant performance gains on these challenging vision-based robotic manipulation tasks. Now, one last aside that I'd like to mention is actually to highlight a paper here at ECCV that tried to solve a similar, tried to extend this work, but instead of leveraging demonstrations, looked at using videos of humans in the robot's environment in order to help solve these tasks. And very briefly, the gist of this approach is to simply augment the predictive model with latent variables that capture the unknown actions that the human took, as well as domain shift between the human and the robot, because the human doesn't look like the robot. And overall, the robot was able to use both seen and novel tools by using this video data and without any demonstration data using tools. And we also saw kind of a significant increase over SAVP, which is a video prediction model that isn't able to leverage these videos of humans. And of course, the success rate here are a bit low, but these are also extremely challenging tasks that require picking up an object and using that object to manipulate other objects when the robot is only given raw pixels as input. Great. So to conclude, I talked about 3 approaches for exploring in a structured manner without reward engineering in a manner that is hopefully that's really more practical for real-world robotic embodied learning settings. And in each of these cases, we looked at leveraging easy-to-provide supervision and robotic experience for learning multiple complex vision-based tasks. I'd like to thank my students and my collaborators who played a large role in all of this work, of course, and hope to see you at the panel. Thank you.